Go. Hello and welcome back to Calculus 2, section 10.6 on the alternating series. So for this one is probably one of the easiest ones to spot because it has the alternating term in it, which is the good old negative 1 to the n, or some variation of it. So we will start with the. Oh, good thing. This is. Right, thank you. So what do we have, guys? For alternating, if I have negative 1 to the n, and then I have, let's say, n. Now, this is alternating sequence, which would, if n is equal to 1, you have negative 1. When n is equal to 2, you have a 2, and then a negative 3, and then 4, and then negative 5. So you see the importance for computer science if you need to define a formula that will alternate terms as they rise, right? So you multiply negative 1 raised to the n by n. And can you switch it around and have it as negative 1 to the n plus 1 times n, in which case you are going to start with 1 and then negative 2 and then 3 and then negative 4, then positive 5. So you can swap all of the signs and be like that. Now, the graph of these, right, are going to alternate on opposite sides as you go 1, 2, 3, 4, 5, 6, right? They keep jumping from one side to another. That's why they call alternating, right? Because it's either positive and then negative and positive and negative, positive, negative, and so on. So now, we would like to discuss alternating series and see if those converge or diverge. And we're actually going to have now convergence split in two. We're going to have something that is called conditional convergence and something is called absolute convergence. And those now will be a little bit different than what we have done so far. So for our alternating series, we have this negative 1 to the n a n. It starts at any value, 0, 1, 2, whatever, doesn't matter. And this is called alternating series because you can see the alternating piece. So now, for alternating series, there we go. We have to have some conditions fulfilled so that we can test for converge or diverge, right? So in order for it to converge, first off, if you look at your sheet, you will spot that the divergence box is empty, meaning that this test is not meant to look for divergence, but then things could diverge, right? Problems can diverge, so it's okay. So what do I have? This is more like a tree diagram of procedures that you go through. So you start from your problem that it's given to you, and then you look only at the sequence an. So you disregard the sum, you disregard the alternating term, you completely disregard those, and you just look at the sequence an. And then you can have two things happen. The an could be with a limit of 0. So limit an equals 0 as n goes to infinity, and decreasing. And if that's a yes, we go into the convergence pile. And if it's a no, it's most likely going to diverge. Once you go to a convergence pile, you will then take a look at summation of AN. Again, no alternation, guys. No alternation here. We just look at the series of AN. Now that one can converge or diverge by any of the 9 tests. If it converges, we reach something that we call absolute convergence. And we denote that with AC. And then, if it diverges, it goes into conditional convergence, which is a CC. So please note that this branch that goes to the left is the convergence branch, right? So this is our convergence branch, and if your problem ends up in a convergence branch, then depending on convergence and divergence here, it's either going to end up being a conditional absolute convergence or conditional convergence. You're making movement. So now, what do we do? Well, let's just take a look at the best problem, in my never humble opinion, to describe and explain conditional convergence. We are going to take a look at alternating harmonic series, which is -1 to the n divided by n. You can start at 1 and go to infinity. You can start at 10. It doesn't matter. You can't start at 0, right? Because you would have divided by 0. But you can start at 1 or any other value. Now, is this alternating series? Yes, because you look at it and you see -1 to the n, or -1 to the n plus 1, or so on, right? So that's very important. We immediately spot its alternating series because we see it is alternating series. Your immediate response is to fish out AN. So you are taking the -1 to the n away, and the leftover is AN. Now remember the 2 conditions. One condition is that your AN has to be decreasing, and your other condition is that the limit has to be 0. If both of those conditions hold, you are on a convergence branch. So, limit of AN, which is limit of 1 over n, is equal to 0 as n goes to infinity. So that condition checks out. The next condition is that you can have this to be decreasing. Is it decreasing? Of course it is, right? What are your terms? Decreasing? Your terms are 1/2, 1/3, 1/4. Well, that's decreasing. So, is it decreasing? Yes. So, both of the conditions are okay, which means we are now on the convergence branch of the tree up there, right? So you can see you start with a problem, you fish out your AN, and if both conditions pass, you are on the convergence branch over here. All right, so now that's all taken care of, and the next step is for us to check convergence of the AN alone. So the next step is to do the convergence of AN, which is what is the convergence of 1 over n as n goes from 1 to infinity. Now, what do we know about this? It diverges by p series or by integral test, very good, or by, we just know it's harmonic series, that versus you memorized it, right? By memorized it. So harmonic series 1 over n diverges. So now, answer. Since an is decreasing and converges to 0, that's a sequence. And summation of an diverges the series summation -1 to the n over n conditionally converges. So now this is going to be the time for us to understand conditional convergence. See, absolute convergence is your good old convergence that you had so far. Why is this one called conditional convergence? Well, we found out that the problem summation -1 to the n over n jumps on the convergent branch. So it's convergent in nature. But then we also know that if you remove, right, so if you have this alternating term, it's convergent. If you remove alternating term, it's divergent. So you see how the name conditional convergence fits? Under condition that alternating term is present, it converges. Without that condition, it diverges, right? So that's the case that we are. So this is a conditional convergence. It's convergence, but it's conditional convergence, which means that if you remove this part, you get this and it diverges. So that's the reason why it's called conditional convergence. It's interesting. So now all we need to do is to do, 5,000 examples. There is nothing else to this test. The steps are already laid out to you. Take away the sum, take away alternation, you are left with an. Check for the limit of 0. Check for the decreasing. If it passes both conditions, then do the summation of an using any of the previous, any of the other 9 tests that are given to you. And then, well, we didn't cover the last 2 yet, but we will. And that's it. So it's a very structured approach. You just need to follow all of the steps. So one more time, when you see the alternation term, you know it's alternating series. You take that away. The rest is an, and then check the limit to be 0. Check that it's decreasing. If those two are both correct, both satisfied, you are on a convergent branch. You just need to decide whether it's alternating or conditional convergence by, dare I say simply, figuring out summation of an using any other test that you learned before. So that can be literally anything. So now I'm going to jump into the textbook and pick up some of the homework exercises. Oh, by the way, before we do that, do we all remember the other way to denote alternating? I did give you this, I remember. Yes, it was trig. Good. So alternation is given by -1 to the n, -1 to the n plus minus 1, whatever you get there. And do you remember the cosine n pi? Now, tell me what I should have for sine there to also be alternating piece. Excellent, n pi over 2. Guys, if you see any of these, they are all alternating terms. So star these. make sure that all of these give us alternating series. All right, so let's jump real quick into the homework for chapter 10, section 6, and do another 1 or 2 examples so that we can go and do the root and ratio test, and those are extremely important. So, a problem in the problem 20 in a textbook gives you the summation 0 to infinity of negative 1/5 raised to the k. What is this without the negative over there? Geometric series. So this is geometric series without the negative. Because we have a negative, we can massage this with algebra a little bit to get negative 1 times 1/5 to the k from 0 to infinity. And then this splits into negative 1, it gets its own k, and then 1/5 gets its own k, because this is just basics of algebra, right? So there it is. I see the alternation using some of the basic algebraic manipulations. So all I need to do is to focus on my AK. So AK is equal to 1/5 raised to the k, and I need to show those two conditions. I need to show that they hold if I want convergence, right? So limit as k goes to infinity of 1/5 to the k is, I hope you all agree, it's 0, right? Because you have 1 to the k, which is 1, divided by 5 to the k. When k goes to infinity, 5 to the k goes to infinity. 1 divided by infinity is 0. So the condition for the limit is 0 holds. By the way, I taught yesterday in Calc 1 L'Hopital rule. We are going to run into problems in the next section. So take a look at that lesson from last night. If you need to refresh L'Hopital rule, I did all of the cases: 0/0, infinity over infinity, infinity minus infinity, 0 times infinity, 1 to infinity, 0 to 0. So, when k is infinity, right, you get 1 to infinity, which is 1, and you get 5 to infinity, which is infinity. 1 divided by infinity is 0, right? Good. The next one is decreasing. So is it decreasing? You can just write out, and then 1/25, and then 1/125, and then 1/625. Well, you see that this is going to 0, and it's keep getting smaller and smaller and smaller. So yes, it is decreasing, because it's a cheap problem.
I imagine for slightly more complicated problem, just take a derivative.
Yes, and that's the next example. Perfect. Yep. Guys, both conditions are satisfied. That means that we are already on a convergence branch. All I need to check now is the summation of 1/5 to the k. What's happening with this? What's happening with this? Come on, converge or diverge, and by which test? Converge by geometric series. Converge by geometric series. If you are not still getting this, your R is 1/5, which is less than 1. So it's in a convergence if you look at your Second row on a sheet that I gave you. Second row. So answer. Since AN converges to 0, I'm talking sequence talk right now, and AN is decreasing, and summation of AN is convergent, the series summation of negative 1/5 everything to the k from 0 to infinity converges absolutely by alt series test. So we looked at the sequence to come up with the decreasing part, and we looked at the sequence to come up with the limit is 0. Once we have those two pieces, we look at the series. And as you can see, the entire calculation, 100% of the time, ignores the alternating term, which was negative 1 to the n. So we don't have to worry about that. Exactly. All right, so now, ready? One of these, everyone, get your wrist going. We're going to do one more example of alternating, so make sure, get some finger action there, so like this, so you can get the blood going into every, yes. All right, so now that you work this out, shake it off, shake it off, shake it off, and now we have a problem 24. Summation from 2 to infinity of negative 1 to the n divided by n times ln squared n.
Is CA the same thing as AC? Like absolute?
Absolute convergence, absolute convergence, or converges absolutely. So ACCA, whatever you put. And then you have a CC for conditional convergence. ACCA. Why, did I switch it? Oh, convergence absolutely or absolute convergence. Yeah, I used AC before, so here. AC, fine. Are you ready? Oh, you look at this problem and you see that ln squared and lock the doors. What do we do? Well, the first order of business is to get the AN, right? And the AN is everything except the alternating term. So 1 over n ln squared n. And we have to check our two conditions, right? So condition number 1 is to show that the limit is 0. So limit n goes to infinity of 1 over n ln squared n. Okay, so all I have over here is 1 over infinity times infinity is 0. Just by looking at it, it's 0 because you are dividing 1 by infinity. Both n and ln are increasing functions, so when you plug in infinity, it just goes up forever, so 1 chopped up infinitely many times is 0, so we're good to go. Second condition on decreasing. So now this is where the derivative is going to help us. Because, I mean, we could do the direct comparison. So how about I do both? Let's do derivative. So the derivative, remember to change this into x, because we are looking for, right?
You can't just say dn.
No, because it's discrete. Derivatives work over continuous functions, right? So what do I have? I actually have the derivative of x ln squared x to the negative 1. So it's going to be a double or triple chain rule with a product rule inside. So it's fun. We go with the negative 1 times the guts times to the negative 2. And now the derivative of the inside, copy the first, which is x. The derivative of the second is 2 ln x times the derivative of ln x, plus copy the second, times derivative of the first is just 1. So a little bit convoluted there, but it works out. So we have this denominator of x ln squared x, everything squared. We do have a negative 1 on top. And now these x and x will cancel over here. Bye-bye. And all I have is 2 ln x plus ln squared x. Now, can you just look at this and know it's always negative? Denominator is squared. So denominator will only give us positive numbers. In the numerator, I have a function whose values are all positive after 1. But our domain starts at 2. Right? So your ln function looks like this. And you clearly have negative values for y between 0 and 1. But we start counting at 2. So we only care about this part of the function. So now that we established that all of these are positive and they're added, what you have is negative 1 times a positive value divided by a positive value. All together is a negative value less than 0. Well, we know that's decreasing. So we put the green check mark there because it is decreasing, because we got the negative derivative on the entire domain. So that's one of the ways to take the derivative. Other way to get the same thing would be to define an plus 1. So if your an, right, if your an is 1 over n ln squared n, so this has to be n plus 1 ln squared n plus 1, because that's the next term. So this is the next term. So now need to show that an plus 1 is smaller than an. So this is what you need to show. If this inequality holds, then the function is decreasing because the next term is always smaller than the previous term. So that should be like this. This equation here should be common sense. It shows that the next term is smaller than the previous term, so it's decreasing because it holds for all terms. This is an, right? An is taking n1, n2, n3, n4, n10, and 100. So you bring in your an plus 1, which is this long thing we have. And that needs to be smaller than 1 over n ln squared n. So when you cross multiply, you will get n ln squared n smaller than n plus 1 ln squared n plus 1. Do we see that the terms on the left are smaller than the terms on the right? So it's good. This is more like a direct comparison thing that we did. So you're comparing it. Now, my preferred is obviously the derivative. But then you might want to shovel the expressions like this. It's okay. right? So, what am I having now? The first condition has passed, the second condition is passed, and all I need to do is to look at the summation of 1 over n ln squared n and see if this converge or diverge. If it converges, we have absolute convergence. If it diverges, it has absolute divergence.
Show that it was decreasing.
To show that it's decreasing, the two conditions, right? So you can do the decrease either with the derivative or with the blue stuff. I gave two ways of showing the condition on the decrease. If you look at the sheet I gave you, alternating series under conditions for convergence, the first line with the an plus 1 less than or equal than an, that's the conditions I did in the blue. As the alternative to that, you can take the derivative and make sure it's negative, and then condition underneath that the limit goes to 0, right? All right, what now?
Skip to chapter 10.
What kind of test is this?
One that we're all going to fail.
Are you?
Are we done?
Integral. You can integrate this. You can integrate this, right?
Why?
Do you see your ln and you have its derivative 1 over n available, so the whole thing becomes just 1 over u squared?
Mm-hmm.
Yeah, it's obvious, right?
Oh, yeah, obvious.
So we do integral test. Now remember what you have to do for integral test? The 3 conditions, and then you can do integral test, which is impulse. So you remember what we did at the beginning of this problem? We have to stretch the ligaments and muscles and everything in our, because now page number 2 for this problem begins. Integral test. We define a function f of x as 1 over x ln squared x, and we need to show those 3 conditions for integral test. The good thing is we already showed one, right? Number 1, continuous. Okay, this is where you write the proof that you learned in Calc 1. You say x and ln x are continuous functions. Guys, that's a theorem in Calc 1. You call on that theorem. Exponential functions are continuous, sine, cosine continuous, polynomials continuous, which is x, right? Now, function combinations and function compositions of continuous functions are continuous. That's another theorem. So, function combinations and function, what's going on over here? I can't scroll. And function compositions of continuous functions are continuous. So we just proved it. Oh, no, one more thing. We have to also show x ln squared x is different than 0 because we are on 2 to infinity domain. So you can't get 0 in denominator because we have a rational function over there. It's 1 over, right? So you also have to show that the denominator is not 0, because if denominator is 0, that's a vertical asymptote, and that is not continuous, right? Vertical asymptote interrupts your day. Just try to leave the classroom through this wall and see what happens. Right? It's called the vertical asymptote. So what do you have? You first take a look at each individual function. That's x and ln x. By the theorem in Calc 1, those are continuous. What else do you have? You have a function composition because you are composing x squared and ln x. So that's the composition. And you have function combination, multiplication between the polynomial and this. So combination is multiplication, composition is a square on ln. So now what you proved is that the denominator is continuous. 1 is just a continuous line across, right? So continuous, 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 and as a group continuous. The only thing that you need to show now is that the division over here is continuous, which means you are not allowed to have 0 in denominator. So denominator cannot be 0 because your x, the lowest value x can take is 2. So at worst, this is 2 ln 2 squared, right? So you are not in the danger to create 0 in denominator. So now we have proved that the function is continuous. The next part is decreasing. Well, that's done above. We just did it. You can do the blue or the black. I don't care which one. So we just check that one off and say done above as we were proving the continuity. Third condition for integral test is very good. Is it positive? Well, you argue the following way. ln x, everything squared, is always positive because the answers for the square are always positive, right? X is always positive. Why? Yes, because, very good, because we are on 2 to infinity. Excellent. So we proved that both of those pieces, and now what do you have? You have positive divided by a positive times a positive. That's equal to a positive. So we just get to check this off. We're done. So all three conditions for integral test hold, which means that we can write our integral 2 to infinity of 1 over x ln squared x dx. This is limit x goes to, not x, sorry, b goes to infinity of 2 to b of, and now you have 1 over x ln squared x dx. We already said this is a basic u sub. U equals ln x. du equals 1 over x dx. So we will have to go back to x, so I'm going to keep my limits and all of that stuff. Integral 2 to b. I shouldn't be using 2 and b. I should switch to u, but I have u to the negative 2 du. Limit b goes to infinity of the integral, no, integrate now, which is u to the negative 1 over negative 1, so negative 1 over u, calculated from 2 to b, but I need u to be x, so that's ln x there actually, ln x. So now, plug in the limits. I have limit b goes to infinity, and then I have negative 1 over ln b minus negative 1 over ln 2. When I plug in infinity for b, what do I get? I get 1 divided, so I get a 0 plus 1 over ln 2. that converges. So we got the convergent problem. So now answer. Since AN converges and AN is decreasing and summation of AN converges, the series summation of -1 to the n divided by n ln squared n converges absolutely by alternating series test. Now, the boss move.
Olga wants you to label the steps.
What?
Olga wants you to label the steps.
What steps, Olga?
I don't know.
There are no. Oh, well, yeah. This is a problem that took like a year to solve.
Can you go through and explain now that you have everything?
Now that I have everything written, okay. So let's go through this problem again from scratch.
Can you explain first why, the problem that you did before this, we didn't have to do it, we didn't have to integrate it?
No, because problem before was a geometric series test. Now you have the integral test. Because the series of AN is whatever falls.
So the alternating series test has other tests within it.
Within, yes. And it could be any of the other 9. Just like you have, guys, remember how you did improper integrals? And anything can be an improper integral, right? The improper integral was just a shell with the limit in front, whether you have a vertical asymptote or infinity in the limit, right? But the integration inside could be u sub, could be trig sub, could be fractions, right? Anything. So alternating series test has the similar kind of feel to it. You get to do these two first, right, to prove that the limit is 0 and to prove that it's decreasing, which is what alternating series require. If you pass those two tests, right, you are on a convergence branch, then you have to test series of AN. This is where any of the other 9 can kick in. It's a very, very systematic.
So how do you know which one?
It's called experience.
Yeah, but
That's
you only have 1 week until it tests. You don't
Yeah.
have much time for experience.
Exactly.
So what does that?
There is absolutely nothing that I can do about that. I understand your pain, and as I said in class, if you score more than 68 on this exam, you did better than I did when I took this exam. That's all I have to say. All right. So now
It'll be on the final.
Yeah, but this will only have 1 or 2 questions on the final.
So, all right, guys, let's go one more time. So you see it's alternating problem because you have alternating piece. You immediately extract AN, and then you test the two conditions. One condition that AN in a limit has to go to 0, and the other condition that AN is decreasing. Once we proved both of those and we got a pass on both of those, again, I did the black and blue. That's just 2 different ways to do decreasing. You can either use the derivative or you can use the comparison, whatever. So we did the decreasing, and now, or maybe this is what Olga was talking about. Like number 3 is to show what summation AN is. So now summation AN. Well, you said integral test. Okay, I can do integral test, but to do integral test, we have to show 3 conditions before we can do integral test.
So we don't have to do integral test?
Actually, we don't.
So what could we have done instead?
Comparison to P series and be done in 2 lines.
Then why don't we do that?
Oh, it's good to review integral test,
No.
right? Yeah, it's good for experience, exactly, right? Remember how I said experience? So we did condition 1, condition 2, condition 3. Now these conditions here are all conditions for integral test to be done. And then we finally do the integral test which converged. And now we can write the answer to the problem 2 pages later.
So you would get the exact same answer using the other.
Comparison to p-series, yes. So here we can, let's go again, let's go green now. No, green. Orange. So I'll put the orange star over here, and I'll go with the orange star over here. Instead of integral test, we can use comparison test to p-series, and that would speed up the process of this insanely. You have your summation 1 over n ln squared n. Now we compare ln n to square root of n. Well, that significantly changes things, because now you have summation 1 over n square root of n squared, which is summation of 1 over n squared, which converges by p-series. Hello, mathematics. And in order for us to show this, we just need to show that you can use direct comparison, you can use the limit comparison to show the dependence, right? The condition passes, so that we can use this one.
What's a case where you couldn't use comparison?
It was when it was a negative sign, and then
yeah.
no, the direct comparison. Limit comparison usually plows through everything.
Oh, limit comparison does plow through everything.
Yeah.
Oh, okay. So you can skip right.
But again, you have to take the limit. So do you want to do algebra or do you want to do calculus, right? Because direct comparison is algebra. You are shoveling n's and inequality. The direct comparison is doing the limits, which you might end up with L'Hopital rule, and the L'Hopital rule can turn into a logarithmic L'Hopital rule, and then, yeah.
Does this series reappear in Calculus 3, or is this like discrete math, or where does this come up again?
The series? Okay, so first off, the series will be in our next chapter for power series. Then differential equations will have an entire chapter on solving differential equations by power series. And then later on, when you get out of this school and you go to next school, you have courses on Fourier series. So if you're electrical engineer, if you're a math major, there will be Fourier series, Lens series, whole bunch of stuff. But if you're electrical engineering, this is your life. This is the only thing you're going to see later on. There are no x's and y's in continuous. It's just series, power series, and Fourier series, and then from complex analysis, Lorentz series, and with complex numbers in it. So those are fun because they can converge into a spiral to a point. So those are fun. All right.
So why?
And if you're a mechanical engineer, just don't worry about it.
Or
I
if
see
you take
people-
chemistry, you don't have to worry about it either.
Yes, I see people switching majors right now, as we speak, right?
But how come you said compare ln to the square root of n?
Because the graph for ln and the
Oh,
graph for
okay.
square root,
I remember. Yeah, you did that. The other
Yes.
day. Okay.
exactly. So they're both. I mean, they're not the same, but
Similar.
it's good enough. All right, it was good enough. So now we can do direct comparison. And for the direct comparison, I need to show that 1 over n ln squared n is smaller equal than 1 over n squared that I'm comparing it to, right? Because this one that converges needs to be bigger to track. Now, if this doesn't work, then I'll do the limit comparison. So what do I have? I have n squared to be smaller, right? This is a question mark still. Then n ln squared n. One of the n's will drop. And the question is if n is smaller than ln squared n. And you can't really show this one because you are comparing a polynomial function to transcendental function, and that doesn't work well in mathematics. So abandon and then use limit comparison. Now, I did tell you that you should use limit comparison pretty much all the time. So you have the limit n goes to infinity of an, which is your good old problem, n ln squared n, divided by 1 over n squared. The limit n goes to infinity, one of these n's dies, and you have n divided by ln squared n. What you need over here is either a 0 or a finite value. You cannot get infinity, right? So now, what do we have over here? Well, when you plug in infinity, you get infinity over infinity. So hello, L'Hopital rule. So this is equal by L'Hopital. Limit, it's by Bernoulli, not L'Hopital, but that's okay. 1 divided by 2 ln n times 1 over n as the chain rule. Right? Right. Yeah, this is not looking good now.
Yeah.
It's n over 2 ln n, and that's infinity. Well, direct comparison didn't work out. We have to stick with the integral test. Tough luck.
So why did I?
Sorry, Olga.
Because we got infinity?
Yeah, you have to get either a finite number or 0 in order for it to converge. Because we have a convergence here on this one.
Wait, isn't 1 over n squared, wouldn't that be less than 1?
This one?
Yeah.
What do you mean less than 1?
For the P series.
No, 2 is bigger than 1. I think.
Where's 2?
Right here.
That's the exponent.
Is the exponent. P is.
Oh, you're just looking
It's
at
1
the
over n to
exponent,
the
you're
p.
not looking at the whole thing.
No. P. If you look at the sheet, right, you clearly have the 1 over n to the p. Yeah, I gotta memorize the sheet. All right, well.
Why can't we use this during the test?
Fail.
We can't use this during the exam.
Why? You just remember it.
It's a little bit to remember.
Which is why only 1% of you are taking this class.
I want to cry. Oh.
So use integral. Unless I made some mistake along the way, but you get the idea that this stuff can be very, very tricky. All right, so where's the beginning? There we go. So guys, for alternating series, you will recognize them as soon as you see negative 1 to the n, or cosine n pi, or sine n pi over 2. Those are your triggers. You get, you separate an, you test an as a sequence, you test an as a series, and you make conclusions about this problem looking at those results. And that's alternating series.
Hold the vote close for no third exam.
Yeah, but we still have to.
All right, so the next lecture, well, we can't vote till next class anyway, because we need to finish this chapter now. So this is it. Next lecture.